Hi everyone. Let's continue our discussion of localization on a fitness peak of a DNA sequence which was considered in terms of zeros and ones, a binary DNA sequence, and let's pick up from where we had left off last time. So I just want to start by re-emphasizing the question that we are trying to answer. If this is the sequence space and y-axis is the fitness. So, this is a highly simplified one dimensional sequence space which is an oversimplified picture, and if we have a fitness landscape such as this, a single peaked fitness landscape, and this represents the sequence which corresponds to the maximum fitness of an genotype which belongs to this sequence space. The question that we are trying to answer is that we understand that at steady state of this system, and if we have finite mutation rates, the steady state distribution of individuals is going to be centered around this peak sequence, and we are going to have majority of individuals belonging to this particular sequence, but we would also have some non-zero fractions of individuals which belong to the neighboring sequences, and we will have a steady state distribution around this sequence which corresponds to maximum fitness. And as mutation rate increases, as mutation rate U increases, the spread around the peak widens. And the question that we want to understand is that what happens if we keep increasing this mutation rate further and further? Do we keep getting into a situation where the spread around the fitness peak just widens, or is there a qualitative change in the behavior of this localization that we see as we keep increasing mutation rate? And to analyze the system, the framework that we had started with the last time round was that we have a sequence of length L, and because we are considering DNA to be binary, this corresponds to a total number of 2 to the power L sequences. So, the stretch of DNA that I am interested in is of length L, but DNA being binary, in this case we have 2 to the power L sequences, and the way we had defined our fitness landscape was that the sequence of all zeros, so this particular sequence is the fittest sequence among all the 2 to the power L possible sequences, and the fitness given to this particular sequence was F naught, and all other sequences have a fitness equal to 1. So, when we say fittest, this clearly implies F naught is bigger than 1. What we had started was that we are interested in developing dynamical equations representing these two groups of sequences, one which represents the fittest sequence with a fitness equal to F naught, and the other group of sequences is all the other sequences clubbed together, all of which have fitness equal to 1. So, then we say that let x naught be the fraction of population with the sequence all zeros. So, this is the fraction of population which is growing at growth rate F naught, the fitness of this sequence, and let x1 be the fraction of population which has all other sequences. And doing that is fine because all other sequences have the same fitness which is equal to 1. And what we are interested in is coming up with dynamical equations, coming up with expressions for dx naught by dt and dx1 by dt. Before we get there, let's try and visualize the fitness landscape that we are talking about here, and what this corresponds to is we have sequence space. Here is my sequence of all zeros. This is fitness, and my fitness landscape is such that this sequence corresponds to fitness equal to f naught, and every other sequence in this plane has a fitness equal to 1. Every other sequence, they are all equal to 1. So that's the fitness landscape that I'm talking about. And again, this is an idealized representation of this fitness landscape, which is a higher dimensional quantity which is being represented in this 2-dimensional plane. We had discussed last time that this being a binary sequence, DNA being binary here, the number of neighbors that this particular sequence has, the one mutant neighbors, is equal to L. But in this highly simplified representation, this sequence has only 2 neighbors, which is a consequence of representing this higher dimensional structure on a plane. But for our purposes, we will consider that these 2 neighboring sequences represent all L neighbors associated with this particular sequence in this hyperdimensional space, which represents the fitness landscape of the system that we are talking about. So now again, this is my simplified vision of the fitness landscape, and we are interested in coming up with expressions for dx naught by dt and dx1 by dt. So how do we go about thinking about coming up with these expressions? And the way we'll start thinking about this is, let's divide this entire 2L number of sequences into 2 groups. And in the first group is just x naught, which is the fraction of population belonging to the fittest sequence, and in the other group is represented by x1, which is all other sequences, fraction of the population which belong to all other sequences, everything except than all 0 sequence. So this one is, we know, is growing at fitness f naught. This one, every sequence is growing with a fitness equal to 1. But this x1 is comprised of 2 to the power L minus 1 sequences, and each one of them can be represented by a node. There are 2 to the power L minus 1 such nodes. The x naught sequence is just one sequence, so that can be represented by one node. And what we have to pay attention to here is that every time a division event happens, what happens in terms of this node and edges diagram that we have over here. And what happens is that whenever x naught divides, if during that division event mutation does not happen, so the progeny is an exact replica of the parent genotype that it's coming from, we get this particular arrow. And every time there is a mutation, the progeny cannot belong to group x naught, the progeny has to belong to one of the sequences in x1. So every time a mutation happens, frequency of x1 increases. If we think about it, which particular sequences in the x1 are more likely to get generated via this mutational event? Not all nodes are equally likely to be generated via this mutation event. And that's so because mutations are typically going to be small, mutation rates are typically going to be small, so the probability that an error is going to happen during the replication event is also going to be small. So all those sequences in the x1 group, so all sequences in the x1 group which are at a Hamming distance equal to 1 from the sequence x naught, are more likely to get generated when this mutation event happens. It's sort of easy to visualize that this group will have sequences which are at Hamming distance 1, 2 and so on and so forth. And those which are at a lower Hamming distance, which means those sequences which differ from this particular sequence at only one nucleotide position, would only require one mutation to happen to this mutant, such that the resultant progeny belongs to one of these in X1. Those sequences which are at Hamming distance 2 from this particular sequence would require that two mutation events happen while the replication, a parent from this group is dividing, and two mutations should happen such that the resulting sequence belongs to group X1 and is at a Hamming distance equal to 2 from the genotype corresponding to the individuals in X0. And those are going to be harder because mutation rates are going to be typically small. So anyway, so when X0 divides, you could have generation of another X0, or you could have generation of one of the individuals which belongs to group X1. What happens in the other case? When individuals in the group X1 divide, again you are going to have a similar process that sort of more often than not, when an individual divides, mutation is not going to happen and you are going to get a progeny which also has a genotype equal to X1. But every once in a while there will be error, and now these errors are going to mean that the progeny can have one of two fates when error happens during replication of one of the individuals in group X1. When error happens, when suppose an individual with this particular sequence is dividing and an error is happening during the process of replication, the progeny, which is a mutant, could either be a sequence which also belongs to the group X1, or it could be a sequence which corresponds to the sequence X0. So we don't know when a mutation event happens for an individual in group X1, where does the mutant go? In this case, because this is the only sequence which belongs to group X0, it's obvious that every time a mutation happens, the progeny belongs to group X1. But when a mutation happens during replication of one of the sequences which belongs to the group X1, we don't know where the progeny lies. And that's a challenge that we have to resolve before we can come up with the dynamical equations which represent this system. All right, let's think about this a little bit more. So what's happening? What is happening is that every time an individual with sequence which belongs to X1 divides, it's going to give me a mutant sequence which could belong to either one of the sequences in group X1, or it could give me the sequence which is the sequence corresponding to the X0 group, which is the fittest sequence. How do I resolve this conflict, and how do I get a quantitative estimate of which of the ones is more likely? So if I look at that, again these are my nodes which belong to the group X1, and this is the node which belongs to group X0. Let's look at one of the individuals which belongs to group X1 such that the Hamming distance between this individual and the X0 sequence is equal to 1. Now we understood that how many neighbors does this individual have? How many neighbors does this individual have? And a neighbor being defined as all those sequences which are at a Hamming distance equal to 1. And that number of neighbors, the number of neighbors is equal to L, because one distant mutants means that those sequences differ from the sequence of this individual at one nucleotide position only, and that one difference could be at any one of the L positions along the length of the DNA. Hence, the number of neighbors is equal to L, and if the Hamming distance between this individual and the X0 sequence is 1, this is one of the edges that's present in the graph, and the other L minus 1 neighbors L minus 1 neighbors of this individual are just present in the X1 group only. So, these number L minus 1. So, now if we sort of ignore the probability of generation of a mutant is going to be smaller if the number of mutations required to go from one sequence to another sequence increases. For instance, it is most likely that when an sequence Xi replicates, you get the progeny has sequence Xi. Let us say that the probability of this happening is P0. P0 means probability that 0 errors happened during replication. The probability that when Xi replicates, you get a sequence Xj such that Hamming distance between Hij is equal to 1. That means during the replication process, you get a sequence where one nucleotide error happened and the other L minus 1 nucleotides were replicated correctly. Let us say the probability corresponding to this is P1, which stands for probability that during the replication process one error took place. Similarly, let us say Xk represents that when Xi replicates, the sequence that got generated was such that the Hamming distance between Hik between sequence I and K was 2, and let us say this is P2, and so on and so forth. Now, we know how mutation rates of organisms are present in nature, and we know that these probabilities are such that P0 is much bigger than P1 is much bigger than P2, and so on and so forth. DNA replication machineries are for the most part very accurate, and they have error repair systems which make sure that not too many errors happen when DNA is replicating itself. So, what that means is that every time an error happens during replication of this individual, most likely that the resultant progeny is going to belong to one of the L neighbors associated with this particular node. So, the chance that the mutant of this parent turns out to be an X0 is equal to 1 by L, which is 1 by L times P1, and P1, remember, is always going to be much less than P0. So, that is a very crude estimate of the probability that when parent of this sequence divides, the progeny acquires one mutation, and that one mutation is such that it leads me to genotype corresponding to the fittest individual, which is X0. This event happens. That is a very crude estimate of that event happening here. Let us look at one more node associated with this, which is at a Hamming distance 2 from the sequence X0. Now, whenever an individual belonging to this sequence divides, more often than not, it is going to lead to a progeny which has an identical sequence as compared to the parent. Should a mutation happen, it is more likely to lead to an individual which is at Hamming distance equal to 1, because chances are if replication process was not entirely faithful, one error would have happened. So, there is a chance P1 that the resultant progeny belongs to the sequences which are at Hamming distance 1 from this particular sequence. This sequence is at a Hamming distance 2, and hence only if there are two mutations happen which during the replication process would this individual lead to production of a progeny which belongs to this particular genotype, and that probability is very small compared to this probability, because P1 is much bigger than P2. The chances that during replication process more than one error happened in in an organism's genome of length L are smaller than one error happening during that process, and so on and so forth. So we can go to each particular node at a given Hamming distance on this group of sequences which is being referred to as X1, and see that as Hamming distance from the sequence X0 increases, the probability that one of the progenies acquires a mutation and a sequence Xi converts to X0 decreases very rapidly as the Hamming distance between the sequence I and X0 increases. So, increasing Hamming distance makes the likelihood of generation of sequence X0 from replication of this sequence Xi very unlikely, which is the trick that we are going to use in our analysis here, that because of this analysis that we had talked about, we are going to ignore that the X1 group could lead to a progeny belonging to sequence X0. This event can be safely neglected. Because this event is going to be so rare, because of this reason that we had just talked about, we are going to ignore this very small contribution of X0 sequences being generated via mutation of sequences which belong in the X1 group. That is a contribution that is very small as compared to, say, this particular contribution, which is number of X0 individuals being generated by division of X0 individuals themselves, and no errors occurring during that replication process. So, this contribution will be very small as compared to this contribution, and hence we ignore that. So, where does that lead us? What that leads us to is, let us go back to the node and edges diagram and see how can we develop our equation further. So, we have individuals in the X0 group and we have individuals in the X1 group. Now, what we are saying is that when it comes to, we are interested in when is X0 generated, and X0 is generated whenever X0, a sequence individual with sequence X0 divides and there are no errors happening. What we are ignoring here is when an individual belonging to sequence which belongs to the group X1 divides and mutations happen, and which leads to an individual belonging to group X0. That is the contribution that is being ignored here. And when are individuals belonging to group X1 being generated? There are two ways to do that. One is that when replication is error free, each sequence is giving rise to progenies which are identical with its own sequence. So, you have this particular way of generating individuals with whose sequence belongs to group X1, and in addition you have X1 individuals being generated whenever there is error happening. So, every time error happens during replication of X0, you get an individual which belongs to group X1. Every time an error happens during replication of X1, you get an individual which belongs to another sequence, but that sequence also belongs to group X1. And this is true because we have ignored the generation of sequences to group X0 when errors happen during replication of individuals in group X1. So, if that is the case, then dx0 by dt can be written as x naught times f naught, which gives me the rate at which the individuals belonging to genotype x naught are growing, and this should be multiplied by q, which is the probability that the replication process was error free. So, this quantity represents this arrow x naught f naught q minus phi, which is the mean fitness, times x naught. Because this is the only generation term and we have deaths taking place in the system to account for a constant population size. Similarly, dx1 by dt can be estimated as, first let us account for this arrow, which is x naught f naught, which is the total rate of reproduction of individuals belonging to genotype corresponding to this group, times 1 minus q. Whatever fraction is not replicating faithfully, the resulting sequences are not identical with sequence corresponding to this, is leading me to an individual which belongs to the group x1. In addition, I also have x1 times f1, which is the frequency of this entire group times its own fitness, which we have said is just equal to 1. We do not have a fraction here because we are saying every time a mutation happens in group 1, the resulting progeny also remains in group 1, and that assumption is being enabled because we have ignored the generation of sequence x naught every time a mutation happens when an individual belonging to x1 is dividing, minus phi times x1. So, these are my dynamical equations, and what is phi? Phi is the variable again that we have been talking about, which represents the mean fitness. So, phi is equal to mean fitness, which is x naught f naught plus x1 f1. f1 is just equal to 1. So, this is x naught f naught plus x1, and I know x1 is just 1 minus x naught that is equal to phi. So, now I have my dynamical equations here, and I have a description of phi only in terms of x naught. The next steps, you should be able to guess the next steps in our analysis here. What we can do is substitute this expression for x naught in this equation. That gives me a differential equation dx naught by dt, which will solely be in terms of x naught. Right now we have this phi variable, but we can write phi in terms of x naught. Then x naught will be the only variable which is present in this equation, and that is when we will analyze the steady states and their stabilities associated with this particular equation, and that is something we will start off our next lecture with. Thank you.